Good day, I'm Alan Marr from Geocomp Corporation. I'm going to give a presentation on how we use performance monitoring to help manage risks in underground projects. I am the founder and CEO of Geocomp Corporation, and one of the things that we do is provide performance monitoring services on tunneling projects, deep excavations, other types of infrastructure. I've been doing this for quite a long time, so I've gathered some experience over those years. I'll try to pass a couple of those lessons on to you. We'll talk about what is performance monitoring, why do we do it, how it helps us in risk management, give a few examples, and then I want to give a few pointers on what are the key components in order to achieve a good performance monitoring program. So what is performance monitoring? It's measuring the performance of construction work is a way to help keep it safe and to minimize surprising performances. Surprises usually cost us money in tunneling, and so if we can measure what's going on, we get a better idea of when we need to do something to prevent bad things from happening. We measure the effects of the construction work on existing structures and utilities in order to help minimize the chance of damage to those. If we damage, we usually have to pay or get into a dispute, and that can be quite expensive. We measure performance of our design to compare to design expectations. How good were the designer's assumptions? How are the site conditions actually behaving? And we measure performance to demonstrate that the contract requirements are being met. Many tunneling contracts today limit how much deformation can actually be allowed, and they may limit lateral movements into an excavation, for example, or settlement of the street, and so you're required to do performance monitoring. But they may be required to demonstrate that the regulatory requirements are being met as well. So, for example, there might be limits on how much we can impact the groundwater, and we need to measure that we're meeting those requirements. Performance monitoring is also known as instrumentation monitoring. So the specifications may have a section titled instrumentation and monitoring. Excuse me. And in many ways, it's also can be looked at as structural monitoring, because much of the performance monitoring we do is of a structure. It's of the existing buildings and utilities, or it's of the new works that are being built, or it's of the soil itself that makes up a foundation, and we look at soil as a structure. So what does performance monitoring in construction really consist of? It consists of us making observations and measurements of key performance or key risk indicators to determine when a risk is emerging, how fast it might evolve, and how bad things might become. This is not a common set of words in our industry, that key risk indicators, but this is a session on risk, and so we use the idea of what's telling us that risk is occurring, what's meaningful, that we could then go measure. Then key risk indicator, the monitoring itself may consist of visual observations, instruments that we use to take measurements, tracking key performance indicators that we've identified as a part of our risk assessment activities, but also includes the logging of context, that is what's going on the project, what's going on in the area that's being monitored that may be impacting performance. So we can't just have an instrument with a measurement. We need to know what might have caused that measured performance so we can understand and interpret it. This is a very important element of underground construction today. If we screw up and something goes wrong, the consequences can be quite enormous. And just a couple of examples here you might be familiar with of a collapse in Singapore that actually was being monitored, but it wasn't an effective performance monitoring program, which I'll get into a little later. Quite a long time ago now, we had an issue here in the United States at Dulles Airport where a tunnel being constructed under the taxiway collapsed and killed a person trapped too. And the consequences here not only was the tragic loss, but of a complete delay of a multi-billion-dollar program for years while people figured out how to proceed in a safe manner. So accidents like this can have enormous unintended consequences, which means very significant risks. So a little more on why do we monitor performance during construction on tunneling. Many of the operational risks we face in tunnel construction can develop very quickly with little or no visual warning. And I'll give you an example of that in a minute or two. The consequences can compound quickly. An example of that might be that we have something that seemingly is relatively small, but it creates a significant delay. And if we're on a project in which there are multiple contractors working, those delays may compound into millions of dollars of claims. We use monitoring to determine when key risks are emerging early so that we can implement contingency measures and help manage those consequences. So the whole idea of knowing what's going on and being able to respond quickly saves us time and money. Performance monitoring also provides solid data to help answer questions like, is the design performing as intended? Are the contractor's means and methods working? Are the site conditions giving the expected performance? And are there changes warranted in the remaining work? Should we change direction in order to continue to have good outcomes? In risk management, there's several steps that you'll find people talk about, and this is common across many industries, that the risk management consists of first identifying the risk, then assessing it, then making a plan to deal with it, and then a step that many miss, and that is to actually monitor what's going on so that you can see if risks are actually emerging so you can then control them. Without that monitoring, you really have little warning and no opportunity to control the risks. And I like to think of this as a circle, a continuous circle, because things are constantly changing. These steps, identifying the risks, important that we identify and collaborate with stakeholders and subject matter experts. When we do the assessment, we quantify and integrate all the risks relative to that threaten the project objectives. We formulate a strategic plan and to deal with the threats and opportunities. We then monitor. We develop and track key risk indicators and do this in real time. We control it by taking action and mitigating risks when we need to. So in order to do this, we really need relevant data on performance to be able to effectively manage the risks. Let me give you an example. This is a deep excavation about 40 feet deep in the middle of an urban area with tiebacks. So it's nice, a rather typical secant pile wall with tiebacks. And in looking at its design, our concerns would be global instability. The existing structures are historic, so what kind of deformations are we likely to get from the unloading, from shear created by this unloading, deformations from dewatering, and then the potential of flowing ground and with that loose sand layer in there. So that might contribute to some additional deformations. So if we tried to formulate a risk register for this project, which is a multi-million-dollar project in terms of just the earthworks, we worry about potential failure modes. So a global instability failure, excessive deformations from shear, excessive deformations from dewatering, and then ground loss from flow into the excavation that also could create deformations. And here I just quickly list off an estimate of what the consequences of each one of these potential failure modes might be, what the probability or likelihood of each occurring. And then you've learned already in this course that risk is quantitatively indicated by consequence times probability. And so we have an estimated risk cost associated with each one of these failure modes. They're on the right column. So if we could, how does monitoring play into this? If we had a good monitoring program, we could potentially reduce the probability and or the consequences of the top two risks to low numbers. That is, we could detect whether a potential global instability was occurring and alter the construction course to prevent that. We could do some things to minimize deformations from the excavation. These might require a little extra money, but they're small compared to us being able to avoid these estimated risk costs. So if with instrumentation, a few hundreds of thousands of dollars perhaps on on instrumentation and some risk mitigation costs, we could effectively offset this $1.8 million in this example. I want to take this a little farther because many of you are familiar with that part of the risk register and of a risk, making an estimate of risk, and we put together risk registers that you've already heard about, in which we put the event, the likelihood, and the potential consequences, and we identify potential risk mitigation measures. This is all planned up front, but it's missing a couple of key things. And from my earlier slide, you'll know that that consists of identifying key risk indicators and what's the action going to be should that risk indicator indicate that the risk is emerging. And I won't go through this in detail, but you can get the idea here that in order to be prepared to respond to risks, we've got to understand what we can measure or monitor or look for as emerging indicators or indicators of emerging risk. And then we have to have some indicator to say, okay, when do we implement the contingency plan? Lessons about risk management from this example. It helps show the impacts of uncertainties in a language that we understand, that is time and money. It helps us, the risk register itself helps us rank relative importance of risk events, helps us to quantify contingencies and account for external risk. It helps show the benefits of acquiring more information from measurements, from monitoring, to help reduce uncertainty, or even cause us to redesign to reduce those risks. Helps us communicate to the project team where the significant risks lie and where we might want to do monitoring. It also encourages risk management planning during the construction phase so that we can respond if the measurements show that we are getting unexpected performance. So really this whole idea, if we expand the risk register out to include key risk indicators and limits on what is acceptable performance, it helps facilitate planning so we can monitor and respond to risks much more effectively. Another example, the Boston Big Dig, construction of a tunnel underneath on the left side, underneath this existing highway, which had to stay in service. Massive undertaking, 100,000 plus vehicles have to keep going as we build underneath this in between all these major structures. And so there's a very extensive monitoring program put in to track how these deep excavations were behaving. A lot of diaphragm slurry walls were put in here with them tied back or braced with some pretty massive cross-lot struts. Right up front, it was decided to simplify the performance monitoring so that we would limit any movement of these walls to 3/4 of an inch, at which point that was yellow and we'd stop work. 1.5 inches, that was yellow and trigger alerts. 1.5 inches, we would stop work. So looking at this from what are the significant sources of risk, it could be collapse of one or more major structures adjacent to the excavations. We had many high-rise buildings within the construction impact zone. Major damages to structures, other structures due to failure of the excavate support system. Architectural damage to historic structures, of which there are 150 along the alignment. And then significantly claims by contractors from costly construction delays caused by damage to adjacent structures or stoppage of the work, as we had a lot of contracts back to back. And so any delay would just could potentially compound throughout the system. So I put together a risk register of some of the major risks in this case in a retrospective some years ago. These 4 major performance potential failure modes that I identified in the previous slide, what the consequence might be, and this is just looking at monetary, not at life loss, the probability of an occurrence of such each one of these, and then an estimate of the risk cost being the consequence times probability. And we came up with about $500 million of potential risk to this project should something go wrong in the subsurface activities that impacted these buildings. There were probably more risks than that because we haven't covered lots of things like utilities and damage to the constructed works, but just enough for this example to illustrate that the estimated risk without monitoring was on the order of 550 million, plus potential for significant loss of life and injury. At the completion of construction, we'd actually the project had paid out about $9 million in damages. There was some that accrued a little later on, but when I did this study, that's about what it was. Total cost of monitoring was around $60 million. So you can see that the monitoring program in this estimate has really contributed greatly to keeping those risks under control and limiting the cost of the project from unexpected performance. So it potentially saved $500 million in project risk costs. And this was documented and reviewed with key project members. So I think that is a rough range of what the benefit might have been. You might argue it might have been 400 million, but it's a very significant number compared to the cost of the monitoring program, which was at that time the biggest ever undertaken in the United States. And actually, it was the genesis, I think, of modern monitoring programs in tunneling, in that we were able to start to get close to real-time monitoring and get the real benefits. This is the first project where we started using email to exchange graphs and communicate what was being observed and communicate when contingency measures needed to be implemented. On the right was the completed project, very beautiful and great contribution to the economy and of Boston and traffic flow. Today, monitoring has changed a lot by technology. We have a lot of enhanced technology that allows us to do this real-time performance monitoring. As I said earlier, risk can develop quite quickly, and so if we're going to use monitoring, we've got to be in a position to do it quickly and move the data around and respond when needed. And this is just one of the tools we use. It's an automated total station that I call it a robotic total station because it operates on its own to swing around and look at prisms. Any one of these can look at up to 100 prisms, let's say, pretty frequently, day and night. And we never had that capability 20 years ago. And that data can be pulled in and put into a computer system and delivered back to people who need to know literally in a minute or two. So there are other things that make all this possible. And I think we've lost track of just how technology changes have brought us many benefits in the instrumentation monitoring world. We have inexpensive, highly reliable hardware these days. We have reliable sensors with a lot more capability. We have essentially no cost, high-speed data exchange on smart devices. And we have powerful database and graphic software that lets us track these large quantities of data that come in, reduce them quickly, get them into a graph, send them back out. So literally we can turn around and be able to respond in minutes now, not days of years ago. Another example of this, I'm sorry, I keep rubbing my nose, but something is causing me to itch. The LA Crenshaw line, TBM, called Harriet, assembled here, ready to get to work, and a concern by LA Metro of this is mining under the street, and a concern that we might suddenly get a big sinkhole in the street. So to help avoid that, we put in borehole extensometers, which have a sensor that goes down to within 5 feet of the top of the tunnel. and then it has a connection back up to the street so that we can measure relative movement of the sensor relative to the street, and then with total station at street level, we can pick up what the settlement there is. So we know the absolute movement at that point as the TBM approaches that point and then moves on past it. So this is an example of how we keep track of data. As the TBM is moving from left to right, that sensor shows essentially no movement until the TBM's face gets past the sensor itself. So getting up to it, almost no movement. And then as it passes, we start, in this case, to get quite a bit of movement. And this is one of the points out here. We're well into the job. This ground had been treated, so things are going good. The limits here are 3/4 of an inch. We go into yellow, 1.5 inches we have to shut down and go into meetings and discussions about how to proceed. So once they came out of the treated ground and the better conditions, they got into a situation, it's going well, but all of a sudden a situation where we get up to exceeding that 3/4 of an inch and headed to actually exceeding 1.3 inches and headed to 1.5 inches. Very concerning because it's very expensive to shut down a TBM, stop a TBM. And so we were able to tell them that right away. They were able to go inspect things. They found the machine itself had run out of materials for the tail grinding system. And so when they corrected that and proceeded with the job, here's what we see. Continuing to do the job with less than 1/2 inch of movement from that point on. That piece of data helped convince people the importance of watching the details and led to the successful completion of the project. So why monitor in real time? Damage can occur rapidly with little visual warning, even when things look okay. You saw that example. Everything was fine, and then suddenly we get movements that are about to exceed allowable. The probability of damage can be reduced using preventative actions if we have adequate warning. So that means we're reducing risk. Consequences can be reduced significantly if we have a reliable warning. We can, in this case, they slowed up, figured out what was going on, corrected it right away, and so the consequences were well under control. Had that not happened, we could have had hundreds of thousands of dollars in delays on a daily basis. With real-time monitoring, we can get warnings of emerging risk and we can take preventative actions. So in order to do this real-time stuff, we've moved towards putting all this monitoring on the web and using handheld devices. We now are able to boil down large quantities of information to just what you need to know. And the ultimate challenge for us in using these measurements is to be able to provide more value to all members of the project team. Many contractors think this is a waste of time and money. But if you get in the right mindset, you'll find that you can put this to great advantage to help you manage your own risks, help the job run smoothly. If the job is delayed and disrupted, everybody loses. So we use this I&M to give us warnings of unexpected or degrading performance. It gives us comfort and confidence that the job's proceeding well on an hourly basis. It helps us improve processes and it helps us reduce risks. This is just an example of how we integrate this information today. So we're able to take measurements from machines, we take measurements from sensors, we take photographs, we take field observations and field reports, integrate that all into one large data and information storage system that can be warehoused, serviced, grow to very large either small or very large data management systems that's very responsive and deliver that data out to where it needs to be, whether it be on your phone, a laptop, or a desktop, or a big screen for a meeting. It's just amazing how all this is tied together now and how it works very reliably. This is just an example of delivering these data onto a phone with the same interface that we use on laptops. So people just intuitively learn how to use these tools now all across the job. We have some projects where 50 people might be monitoring progress. The key to make this work is you got to plan it and you got to be prepared to respond. And when we talk about green, yellow, red, this is just a layout of what you do. Be prepared when you cross over the yellow and get into the red. Another key point, and I'm almost done, is the data. You can't just get data in. Somebody's got to take a look at it and say, does it make sense? Are these data good? Get rid of the garbage and the junk, because that does happen. And make sure that you're getting a clean data set that you're then sending on to the engineers, the decision makers, to decide what does it mean and what do we need to do for the job and its safety. So I call about this evaluating the data to get a clean data set that's reliable, push it on to others who then interpret it. The people who take the data may not really be able to interpret it. That's where engineers, designers, contractors have to take a look at this stuff. And we need to put it into a form that they can do so quickly. And so these tests can take considerable time of well-trained people. In many projects, it's not planned well enough to do these two steps well, particularly in low projects. Got to have contingency plans, and these are well-defined actions to take when the instrumentation shows that a response is needed. They need to be done in advance. They need to be made in writing. They need to agree to them, know who's responsible, and then they should be reviewed and updated periodically. I can take the measurements, but if people aren't prepared to respond when they need to quickly, then the whole plan may fall apart. So I've mentioned a couple of times effective performance monitoring. These are the elements that are necessary to really make all this stuff work. You can't have a great program with one weak link. So a good performance monitoring program consists of visual surveillance and the monitoring with instrumentation. It's got to be designed in a way that it focuses on helping to identify and manage risks. To do that, we do it in a systematic way, and I give lectures on what is a systematic way. If you're interested, let me know, and I can even send you some writing about that. Every instrument should have a purpose. Don't put stuff in that's not needed, and we need an action plan to implement when the monitoring program says it is needed. We need champions. I've found over my many years, without a champion for the instrumentation monitoring, it just ain't going to work. Every program needs to have a champion. For the overall monitoring program, for the execution of it, for taking action when such action is needed, and for the budget, because instrumentation monitoring is one of the first things that usually gets whacked if budgets get tight. These champions must be committed. They must buy in and promote the objectives and benefits to keep them aligned with the overall project objectives. They must have respect for roles and responsibilities of the various participants, and those participants need to respect each other, the importance and the value of I&M. They must be champions to achieve success, make sure that there's adequate resources available to maintain operational effectiveness and to use the results. So a question for you, and then this is kind of my last slide. Who is most likely to deliver an effective I&M program for tunneling in an urban setting? This is a growing debate that we have going on. Is the construction manager the right person to do this kind of work? The general contractor, self-performing, we see more of this happening. An electrical subcontractor, we see somebody says instruments, oh, that's an electrician, give that to him. A geotechnical sub-consultant, well, it's underground work, so let's find a local geotech consultant to do that. Surveyor, some of these instruments involve surveying, so maybe the surveyor is best positioned. We have a DBE requirement on many of these projects, so can we get this done by a DBE firm or an instrumentation subcontractor who specializes in this kind of work, working for the general contractor, or an instrumentation sub-consultant working for the owner? Of the lowest bidder. Doesn't matter, this is all just easy stuff, right? So let's just put it out for low bid. These are all different forms. I've worked in every one of these situations, and they have pluses and minuses. I won't say which one necessarily, but it really comes down to which team has the best value combination of expertise, experience, technology, commitment, and price. It's not just price, it's who is going to deliver the job well. Well, thank you very much, and I appreciate your attention and look forward to your questions.